Well, welcome to this presentation on Malleable VIs, or as I call it, Malleable VIs Unlocked. My name is Natan Biesmans. I work at Qplox. I also created G2CPU. More on that in a little bit. Before we get started, a little bit of housekeeping. If you have any questions, feel free to ask them. But if you have a question, just let yourself known so the wonderful team can give you a microphone so everyone can hear your question. If I can answer it directly, I will. If I feel it might go on a tangent, I might say, let's have that discussion at a later stage of the presentation at the end, or maybe separate. So, who am I? I'm Natan Biesmans. I'm CLA, LabVIEW champion. I've been using LabVIEW for over 10 years already. You might know me from some previous presentations. I did presentations on FPGA accelerated computing. I did some presentations on how you run LabVIEW on Android and iOS. I did a ton of presentations on how to easily do GPU computing in LabVIEW. Currently, I'm the main developer or the architect of G2CPU, a toolkit for LabVIEW for GPU computing. I'm a LabVIEW R&D architect at Qplox Engineering. Currently, I'm deployed at IMEC in Leuven. I've done also a ton of work at ASML. And, well, it's a bit of a homecoming. I used to be an employee of National Instruments about 6-7 years ago. Okay. So, before we get into what are Malleable VIs, let's set the stage. So, first of all, I want to discuss what makes LabVIEW unique compared to the other languages, and how can we leverage that when we are creating APIs. So, first of all, there's fast development and verification. It's compiled, so we know immediately if we're doing something we're not allowed to. If we put in a wrong value, if something's incorrect, LabVIEW will immediately tell us what's wrong and point us to it. We have powerful debugging tools which we can leverage. We can set probes at runtime at any point in our program, as long as you enable it in the properties, of course, to actually see what's happening and get the immediate information. We also have execution highlighting, and of course, each function has its own UI, so technically you can verify your functions on their own. And I like a description that someone told me. It has the tools of a scripting language. You can really dive into the separate parts of it, but you do have the speed of a compiled language. Now, another thing is we can create hyper-reusable codes. A single VI can be made so that it can run across multiple CPU types, multiple operating systems. It can run on a real-time system, even on FPGAs, no matter the bitness. So what that means is, if we design a VI well, it means we only have to create it once. I used to call it code it once and code it right, but I recently decided I prefer it actually switched around. Code it right, and you only have to code it once. So let's get into it. Why did I start this presentation? Why did I think, well, Malleable VIs need to be out here? They are an incredibly useful tool. So as I said, I designed G2CPU, a toolkit for LabVIEW to over 300 functions on the GPU. So hundreds of functions, they're not all on the screen. So things like data management, mathematics, linear algebra, statistics, vector algorithms, Boolean logic, signal processing, machine vision, image processing, and file I/O. Those are a ton of functions that need to be maintained, and it needs to be maintained well. These functions also need to support several technologies. They need to support CUDA, well, they're actually supporting it, but CUDA, OpenCL, it supports CPU, the Intel One API. So those functions need to be smart enough to, depending on what you're doing, change their behavior. They need to work in different environments. They need to work in Windows, in Linux, LabVIEW RT without any issue, and preferably without changing your codes. Now, The downside with these functions, and just to give you a sense of the scale, if I wouldn't use Malleable VIs, and that's going to be clear at a later stage as well. So there are a lot of input variations. On every input, I support 13 data types: integers, floating point, complex numbers, wide range. Four dimensions, so 1D, 2D, 3D, and so on. These functions support GPU arrays, so arrays that are already on the GPU, but also functions, also arrays which are made in LabVIEW. It will automatically upload them for you. And just to make the permutations even worse, there's also support for scalars. So if you do a division by 2, you can just feed the scalar in, and it will automatically do the work in the background for you. Now, to give you an idea of what that sounds like in numbers, so a simple addition, just adding two numbers, has over 12,000 different possibilities. Well, if I had to create a VI for each one of those, I think I would be insane at this point. So I consider this a permutation hell if I would have to create each permutation manually. So this is why I landed on Malleable VIs. And this is what I want to teach you guys, the lessons learned, or the lessons I learned when creating this toolkit. The idea here was I wanted to provide a near LabVIEW-like experience where there are broken runtime arrows. There's development time evaluation, so the colors change dynamically based on what you're doing. So the wires also change. There are probes which are running, which is going to pop up in a moment. And of course, how to manage your permutations in an effective way. And of course, even how to do unit tests with Malleable VIs. And there's going to be an interesting slide, which not everyone might have seen yet, which is going to pop up. But so how can we do all this management? So that's going to be this presentation. Why should you use Malleable VIs? Well, I already hinted to it, why I started thinking or why I considered them. But why do you care? So let's say this is normally your block diagram. You can play around with it. You can change data types, dimension counts, and whatever. The basic LabVIEW functions, they will be able to just accept them and change their behavior for you. So Malleable VIs, they are a special type of VI with the extension VIM. And they're a great way for dynamic code execution. So changing the behavior based on certain conditions. They pass through the data types as if the contents of the Malleable VI is just on the block diagram. So it's not like a normal function where it tries to coerce the data type into a specific value. It provides development time evaluation due to this. If you change the data type, it will just be passed through to the contents of the Malleable VI, and it will tell you, well, I could evaluate it yes or no. And what that looks like is, for example, here I have a Malleable VI. This is the block diagram on top of the Malleable VI. I can change the dimension counts. It happily accepts this. And I can even change the data type. And you can see the output also automatically changes. So instead of making a VI for each one of these permutations, I just created one VI that can do all of that in one go. So if you have an algorithm that can scale across multiple data types, across multiple dimensions, those Malleable VIs can do that for you, and you only have to do it once. Now, how can you make a Malleable VI? Well, if you want to show off, you can convert a VI. So you start with a normal VI, you give it a VIM extension, you make it inline, you set the execution to pre-allocated clone reentrant, which is a mouthful. You disable error handling, and then you have a Malleable VI. Or, let's keep it easy, there's a template. So you can just go to New, and just select Malleable VI. Cool. So why should you use them? Fundamentals of Scalable VI. So what are the other building blocks that we have? Well, first of all, we have type specialization structures. These are interesting. Based on these, we can change manually or control the change of the code internally. So we can define multiple behaviors based on certain conditions. So these act similar to a case structure, but then on the development side. We're going to have multiple, you have multiple frames which are going to be evaluated. and they're evaluated in order. So it first looks at the first frame. If it can be compiled, it will say, yes, I will take that code, and I won't look at the other frames, the other cases that are in there. If it can't be compiled, it will go on to the next one and see, hey, can I compile this one? And of course, if it can compile that one, it won't do the other ones. You can do nested type structure or type specialization structures to get even more control. And if you're interested, this is the specific code that is being used if you feed in a normal LabVIEW array into the GPU functions, where it uploads the data to the GPU for you. So you don't have to do the upload manually. If you want to do a scalar, it automatically transforms it into an array with the build array function to then upload it to the GPU for you. So if you're making an API, you can build or embed all that functionality in there without any issue and make it easier for your developers. Now, together with the type specialization structure, you have assertions. So assertions are a way to manually break the code, saying, hey, if this data type, this dimension count, this something is being used in this malleable VI or in this type specialization structure, cause your compiler to say, no, I can't compile this. So in this case, we can say, hey, please only allow certain types, saying, hey, if it's 1D floating point, allow it, otherwise don't allow it, go to the next case, and maybe that can be compiled. There's also a structural type mismatch, which means allow everything except for this data type. And of course, you can do combinations, add multiple of them. Now, LabVIEW comes with a ton of extra functions or extra assertions on top of that, which NI has created for you, which can allow you to say, hey, please only allow complex numbers, please only allow real numbers, integers, and so on, or maybe only allow arrays of a certain size. The VI on top, or the malleable VI on top, for example, is part of the source code of G2CPU, which does the conversion of your LabVIEW array to the correct GPU class for the controls, for the wire appearances, for example. So this is the only place where how should I say it? That logic is implemented. And for the rest, it can be reused everywhere, because malleable VIs can also call other malleable VIs. Now, when should you use them? And I think that's the best question of all. First of all, we need to make the decision who is going to benefit from this decision or this information coming back. If it's our users, we're going to say, okay, it's a runtime evaluation. It's going to be visible in the executable. That's where the benefit is going to be. If it's for our developers, it's development time evaluation. So under runtime, you can see, for example, case structures. We all know case structures. We add a couple of frames, and depending on the conditions, it will go to a specific frame. Now, the downside here is we have to manually add a state for each case. So it's best not to add too many. If you want to add 100 cases in a case structure, it's generally not recommended, even if it's just for maintainability. Beside that, we have LabVIEW classes using parent-child paradigms. The benefit here is, well, we can have an undefined amount of states. During runtime, we can load in different classes if need be and change the behavior based on the child being loaded in. So this is great if you have a lot of states. Now, beside that, we have polymorphic VIs on the development side. So polymorphic VIs are great if you have codes where each permutation is so vastly different, you can't even put them or try to get some common code out of it. So they are great if you manually, so first of all, you have to manually add a state, but they're best for a few states. If you have 1,000, maybe 12,000, like with the addition, states of your polymorphic VI, that's a lot of work, both to create and to maintain, even for a simple code change. And beside that, I think you guys are already seeing the pattern. Malleable VIs, so they're on the other side. They're best for when you have an undefined state amounts, where you don't really want to think about what data is going into it. It's just most data is fine, or only allow classes, or only allow numbers, complex numbers, real numbers, whatever. That's where they're great. So again, great for a lot of states. Now let's talk about classes. So now we're getting into the advanced techniques. Some of the things I figured out creating G-square CPU, which these techniques are also great for other APIs that you might be creating. So the idea here is I have data, which is a car wheel or cartwheel, so a LabVIEW class saying, okay, this is my object. The operator can see it, the developer can see it. They're both a child of the wheel, or a car wheel, and those are a child of a car parts. But we also have a car door. So each wheel is a part, but not every part is a wheel. That's what we're seeing here. So we can use this object-oriented paradigm to make decision-making in our IDE, saying, hey, only allow objects with the wheel, but don't allow objects with the door. They have more flexibility than dynamic dispatch when you use malleable VIs, because we can add more inputs. With the dynamic dispatch, you only have the one input for the class, and the output is going to be the same value. Here we can actually say, hey, I want to have more inputs, make some dynamic decision making, and then on the output, it's even possible to have a completely different class based on the combination that you're going to put on the inputs. It's going to be a nice demo in a few moments. Also, because here we can then, with malleable VIs, constantly reference the children, we can actually give each child a different wire color. So instead of it going to the generic parent, each child is going to be represented for the developer. And of course, each child can also have its own probe. So for example, in the case of G-square CPU, some data types allow images, others don't. So the ones that don't won't give you the option to view the images as they are on the GPU. So here's a quick example. So here I have a car, which is a red wire. I have a car wheel, which is blue wire, cartwheel, toy wheel, all have their own colors. And as you can see here, I have a car, I want to attach a certain wheel to it. On the right, you're going to see the color, which is going to be a new child, a car with a specific wheel, where it's a combination of the two colors. So if I run this video, yep, there we go. I'm going to put down a probe. I see, hey, my car has an issue. It doesn't have a wheel, its own custom probe. And I'm using the attach function. The car wheel is being attached, and suddenly I have a working car. Now, let's say I want to use a different child. So using the cartwheel. So all these are a child of the wheel class, except for the toy wheel, because it's not a car part. But in this case, I have a cartwheel attached to my car. So as you can see here on the outputs, the colors are changing based on the wires. And now let's say if I'm doing something invalid, my developer is doing something invalid, a toy wheel is being attached. Then suddenly you get the decision making saying, hey, this is not allowed. It has the attribute toy or it doesn't have the attribute car, so don't allow it. And the video is looping. So we can use these child parents structures, especially parents, as attributes on which we can query to see, is this allowed or is this not allowed? If it has a parent which is called car, allow it. If it has a parent called toy, don't allow it. Now we can go even way, way further with this, using interface classes. So instead of only having one attribute, we can start adding more attributes. So for example, we have our car parts, we have a car wheel, or wheel, cartwheel, and we can say, well, these also have the attribute. One is metal, one is wood, which are all part of the material interface class, or plastic is also allowed. So we can add more attributes on which we can start querying when evaluating our function. So we get more control. We have even more colors to play with our wires, wider ranges of dynamic probes if we're using the probes on the interface classes. And this is, for example, what that looks like. So the same objects have other attributes as well. So we have the cartwheel, which has the attribute wood. When we burn it, first of all, the wire changes to yellow and black, but we saw a charcoal. The toy wheel, black and green. And if we put a probe here, suddenly we have molten plastic. And then if we want to burn the car wheel, which has the interface class metal, or the attribute metal in this case, you can see, hey, you can't burn metal, so don't allow this. So we can add this cool development level logic for our developers to say, hey, you are allowed to do this, you're not allowed to do that, and you can make it really scalable in that way. Now, to expand on that further, let's just quickly check time. Yeah. So, for example, here we have the infamous addition. So here we are uploading the data to the GPU. We're getting our GPU object out of it. Currently, they're blue. And the idea here is my addition, the output of that, the color, the data type, it's dependent on the combination of the inputs. If I add a floating point with an integer, the output is going to be a floating point. If I add a 1D array with a 2D array, in GPU it's allowed, the output is going to be a 2D array. So let's have a look at this video. Here you can see the wires changing. The output is changing. Same here. So it's taking the biggest value on the outputs. If I change the data type, the output is changing. So it's doing that evaluation using the principles I just said. But it's taking the largest dimension count on the output. Now, how did I do that? Well, I have code for you. So this is how it works internally. This is the actual source code. So what's happening here, I'm doing a quick translation of that GPU object back to a LabVIEW prototype. And I'm actually using the standard LabVIEW functions to get that behavior. Instead of using type specialization to make an implementation for each permutation, I'm just saying, well, these functions already have what I need. Let me use those. So on the left-hand side, the object to proto is just converting the object back to a LabVIEW array. And here, I'm splitting up the logic. So on the bottom-hand side, what I'm doing is I'm removing the array components using the add array elements. There's nothing in that array, by the way. It's an empty array. It's just as a framework for my developer. During the runtime, you're not going to notice this. So I'm using the add array elements to get the actual scalar data type out of it. I'm using the addition in LabVIEW to put them together. So integer, floating point, integer, and I'm going to put that out. In parallel to that, because the LabVIEW addition function doesn't have the functionality I need for the dimension counts, because you can't add 1D array with a 4D array or 2D array in LabVIEW, or the standard functions, I'm extracting that information to the side to then do some other work on it by getting the largest array. We're going to have a look at that code a little bit later, but then on the end, I'm using the initialize array to say, hey, I'm going to merge that back together, grab the biggest value, so using that type specialization structure and saying, hey, it needs to be a 1D, 2D, 3D, and so on. Some other things you can do, for example, the cluster to array is an interesting function. Let's say you want to iterate over multiple items, or you want to make sure that the values my developer puts into my function is all the same. This is a great way to do it. If you do a cluster to array, you can only do a homogeneous setting. So only strings, if you add an integer to that, it's going to be broken. And I have a really nice example on that in a moment. Now, in general, these don't have runtime impact if you follow a couple of rules. First of all, make sure you have your compiler optimization set correctly. If you start messing with them, you might see a different impact. The default is often fine enough. But you have to make sure that actually no data is going through those functions. So here, I'm just doing the translation. It's great. If data is going through it, just keep in mind that you might see a performance impact if it's being evaluated. But in general, as long as you don't use the output values, the compiler is just going to kick that code out anyway. And so you have your framework while actually no compiled code is being used. Now let's have a look at mathematics. This is a fun example. Some of you might have already seen this video. So this is me indexing an array. So when you index an array, for example, if you have a 2D array, I can index a certain row. and the output is going to be a 1D array. If I have a 4D array and I'm indexing on 2 dimensions, the output is going to be a 2D array out. So in this case, I have a 4D array going in on the GPU, and I'm indexing with 1 value, and that's going to be put on the output, so a 3D array. So let's have a look at this video. First of all, mandatory, I have to change the data type to show it nicely propagates. Awesome. But now, I want to index on 2 dimensions. How do I do that? Well, we can use clusters to do that. Now you can see here the wire is broken because now we subtracted 2 from the dimension count. So there's actually mathematics happening during the development time, not only during the runtime. So now I changed it to a 3D, the output is broken again until I change it to 1D. So that's the type of logic we can implement with not that much effort, actually. So first of all, we can use the array dimension count to do mathematics. Just a disclaimer, it's not Turing complete. You won't be able to calculate the square roots of a dimension count. But you can do some basic things. So we can use LabVIEW functions to, for example, to increment our dimension counts. So saying, hey, use the build array, which is going to add 1, or use the index array, which is going to decrement 1. And of course, you can only decrement until you reach scalar. So you also have a bottom line, which you can also use. And we can combine these to create a ton of different functions. So for example, in the previous example, again, this is the actual source code. We can subtract dimensions from each other. Saying, hey, I'm using the index array. I have my left-hand side, which is, for example, 3 dimensions. My right-hand side, I have 2, so I want to subtract 2 from 3. So what's happening is I am using the index value to then go, okay, let me subtract both of them at the same time, decrement. I can still compile, great. Decrement 1 further, so I decremented 2. And then suddenly, I'm hitting in the scalar point. So if I then want to decrement further, it can't, it's a broken runtime arrow. So it's only going to decrement 2 of that array. Same for the other way around. So if I want to subtract, let's say, 2 from a 1D array, I will be able to decrement 1, but I can't go further. So we have a nice bottom line safeguarding us for, well, negative numbers. Or if we go back to the addition, we can search for the greatest dimension or the biggest dimension, saying, hey, I have 1D on one side, 2D on the other side. Well, what we can do, for example, is create 2 states or 2-type specialization structures, cases, where, for example, we have the left-hand side, right-hand side, and we're going to assume the left-hand side is the biggest one. So what we're going to do is we're going to increment 1, checking if they're the same with that assertion block from NI. If they're the same, are they the same? Yes, no, no. Add 1 more, add 1 more. Suddenly they're the same, great. But what if the other one is bigger? We keep on incrementing and nothing's happening. Well, here we're constantly adding until we reached 4 dimensions. And then we're saying, well, we're at the end. We're not supporting more than 4 dimensions. So it means the other one is the biggest one. So that's how you can implement that type of logic. We can also use mathematics. So you saw me using clusters on the index array. Well, first of all, it works a lot better for our developers than, for example, to provide the dimension counts on the input of an array or of a function. It's really difficult for people to then go, oh, okay, I'm going to go to 3 dimensions, but I also need to fill in values saying, hey, I want to index in this dimension. So we can use the clusters. So here on top, we are converting them to arrays, so we can iterate through them, grabbing the correct values out of them. But in the meantime, we can also convert them, or we can check, okay, how many are in them by just asserting, checking, is there 1 element in there, 2 elements, 3 elements, 4 elements? That's that pink wire going to the top. To then say, okay, I'm going to convert this to an array, and then do that subtraction. So yeah, we can convert it to an array of numbers, or even an array of clusters, if you want to have certain edge cases. Debugging. So debugging is a contentious item with Malleable VIs. They're not the easiest. So first thing you can do is you can convert the VI, or the Malleable VI, to a normal VI. What that actually does, is when your Malleable VI is on your block diagram, it's going to freeze it in place, saying, well, you have these inputs, you have these outputs, and it converts it to a normal VI. What you can do then is you can double tap it and you can start looking into it, seeing, hey, I added this data type here, I added that data type there, why am I not getting the correct data type on the outputs? Or why I'm not getting the correct class, or why is it not accepting this data type? By freezing it in place, you can open it up and actually scroll through the different type specialization structures to see, yes, this is why it wasn't working, let me just quickly change it, great. Also, if you freeze it in place, you can place down probes. You can see, okay, what is the data doing through it, or going through it doing? So the Malleable VIs, I'm mainly focusing now on the development time behavior, but you are also going to put in your own logic, your DLL calls, your visa calls, your image processing functions. So with that, you can still hook into it and see, okay, why am I not getting the response I'm expecting? Now, caution. So they're not the greatest. Any change you make in that converted VI is not going to be taken back to the Malleable VI. So you will need to copy that back over. Also, the function won't dynamically change anymore because it was converted to a normal VI. So you have to change it back into your Malleable. Sorry, you have to move your Malleable VI back into your block diagram, replacing that value. Next up, we have Project Bedrock, and I'm actually really proud on this one. So unit tests with Malleable VIs was not really possible. And while I have 12,000 permutations, I want to give you guys a great product. I need unit tests. So I created a test framework for Malleable VIs, which you can download freely online. It's free and open source. You are free to download it, free to mess around with it, free to do whatever you want. And with that, we can actually test the behavior of our Malleable VI. Verify, hey, if I put this value on the input, can it be compiled? And is the output data type what I was expecting? So I'm still doing further development on it, but it's already perfectly usable. And how it works is, well, it cycles through states in our conditional disable structure. So we are adding symbols to our conditional disable structure. And what the tool is going to do here is this is going to call the VI. It's going to tell LabVIEW, please recompile it with these conditional disable symbols. And then the correct case on top is going to be used. So you can have with integers, multiple dimension sizes, multiple classes without any issue. And then after that, an assertion is being done right here, saying, hey, are these data types equal, yes or no, and then putting it back out. The benefit of this is you only need a single test harness, so you don't have to create a test harness for each permutation or a set of permutations. We can use multiple structures, multiple variables, to actually create test vectors. So for example, if I have variable A, which has 5 cases, and I have variable B, which has 10 cases, I can then, for example, use double for loop to say, test case 1 10 times on those 10 other cases, go to 2 10 times. So it scales quite well. It has support for JKI Karaya framework, unit test framework, and it also supports the NI unit test framework. If you download it, there are examples available to show you how to actually use it. Okay. So I've actually gone through it quicker than I thought. So wrapping up, Malleable VI Quirks. So Malleable VIs, they have a little bit of a mythical status. You can't do this with it, you can do that with it. So I want to quickly pull those in. So first of all, Malleable VIs and PPLs. So a lot of ink has been spilled on this one. So you can use Malleable VIs with PPLs. That's not the issue. You can use them internally in your PPLs. The problem is a PPL, it cements your VIs in place because it compiles them. It contains the compiled code. So your Malleable VI can't change its behavior anymore. So you can use Malleable VIs in PPLs. If they are used within that PPL, then there's absolutely no issue. If you want to use them out of the PPL, yeah, that doesn't work.
What is PPL?
Come again? Someone had a question?
What is PPL?
Oh, so
What is PPL?
Yeah, so PPLs are packed project libraries. They're a technique in LabVIEW in which you can compile your code and actually distribute the compiled code rather than the raw source code. Also, memory usage. I hope someone from NI R&D is in here so I can give my little rant. So memory usage on disk is a little bit of an issue. So when you create a malleable VI, and I learned this the hard way, a copy of that malleable VI is actually stored in the VI that's calling it, or the malleable VI that's calling the other malleable VI. So that's not an issue if you're only doing that once, but if you're doing a stack, well, the malleable VI that's calling this one has a copy of that one in there, but if you have one up, you have another copy, and even the worst thing is if you have multiple copies on your block diagram, you have multiple copies in your file. So if you're not careful, it is possible that you can create VIs where if you just put two functions on the block diagram, that suddenly your VI is 50 megabytes. So watch out. And if anyone from NI is here, please remove that. It doesn't make sense. Next up, sometimes the compiler says a malleable VI is broken or your code is broken. Well, it shouldn't. The logic is there. Now, this is no longer really an issue in 2024, or version 2024, but I've seen this behavior in LabVIEW 2020, 2019, 22, and even 23. So sometimes it can happen that the compiler gets confused, saying, hey, you can't do this. While you're going, well, this was working a moment ago. Why is it suddenly not working? And then you click mass recompile, so Ctrl-Shift and click the play button, and then suddenly it magically works again. Or you close the VI and you open it back up again, and suddenly it magically works again. So it's a quirk in the older version. Please keep that in mind, that if you're seeing that behavior and you're going, this doesn't make sense, mass recompile or reopen the VI, and normally it should be fixed. Also, one last thing, probes don't update when the state of a wire changes. So let's say you place down a probe on your class, your car with a wheel or a cart wheel. If you place the probe and suddenly you change the wire to a cart, it doesn't update the probe. So when you then start running it, luckily it doesn't crash LabVIEW, but what's going to happen is the probe is just going to be unloaded from memory, and it's like you have no probe there, so you have to manually click it again. So please keep that in mind when you're testing and you're going, hey, why is my probe constantly dropping? That's the reason. I also learned that the hard way. So yeah, those are a couple of quirks. If you have any other quirks, let's hear it in the Q&A. So I'm going to wrap up here. So we have some Q&A. If anyone wants to have a look at the actual source code of G2 CPU, now's the time. We can have a quick look. We can go deep into it. For the rest, if you want to know more information, have a look at LinkedIn. You will find me there. If you have questions, if you want to have a chat, if you want to have a sparring session, please do. I love this. I can be found on GitHub. A lot of other projects, examples on how to run LabVIEW on Android and iOS are also on there. VIPM, if you want to use the toolkit that you just saw, just search for G2 CPU and get started with GPU computing. I saw a question.
Yeah, so I'm glad you brought up the size on disk issue. I ran into that as well. I have a whole bunch of malleable VIs for a lot of reuse code that I have, especially FPGA logic that I spam all throughout my FPGA design. So it's been a great tool for sure. But one of the other problems that I ran into, besides just the size on disk, was that it made like my top level design so big that it would take 5 to 10 minutes just to open that VI once the project is open.
Exactly.
So it's more than just...
I actually forgot to bring that up. So because it's so big on file, the interpreter or the reading of the VI is taking so long because it's trying to make all those associations when reading it. And so if you have a 50 megabyte file, it's a real 50 megabyte setup that is trying, or a block diagram that's trying to read in, even though actually it's not doing anything with those malleable VIs that are on disk. Because if you remove the malleable VI out of your project, then it says, I can't compile this, there's broken code. So it's doing nothing with that malleable VI that's stored into the file.
Still looking for the one on disk. So what I ended up having to do with a few of my malleable VIs that were kind of nested and built on top of each other is I ended up having to take kind of the highest level malleable VI and just blow out all the lower levels into just the code. So unfortunately, I lost that kind of reusability of like if I ever have to make a change, those lower level ones, I'll have to go replicate that change in the higher level.
This is actually a little bit more advanced topic that I was contemplating on adding in this presentation. It's an idea I'm playing with using VI scripting to actually allow for normal malleable VI, hierarchical structure. But when I get into my continuous integration pipeline, that it actually just expands the functions, removes the copies or the malleable VIs in there, and just stores them on the block diagram.
Yeah, I like that. So one of the other recommendations I have for, I've run into the same problem of like a malleable VI being broken when it shouldn't be. And one of the ways that I found that I can kind of quickly and easily fix that is go to the VI, the calling VI. I typically operate with separate compiled code checked, but it doesn't really matter, how you use that. If you uncheck it, save the VI, recheck it, save it again, because I found that sometimes the like Control-Shift-Run arrow will not actually like fix the problem. So it's another.
Well, that's the magic of LabVIEW.
Yeah.
But yeah, just a quick question. Have you actually seen this issue also in 2024? Because I haven't actually seen it anymore since I switched over to 2024.
I haven't used 2024 yet, so yeah. I just had a question as well. So do you have any instances of where you have a malleable VI that has an optional input and you want to know whether or not that input has been wired or not? Because I have a few of those instances, and the way that I've solved it is by just making a LabVIEW class that I'll essentially never use for anything else. So I know if it's not that class, I've wired it. And I don't know if you have any better ways of solving that.
Yeah, that's actually also the way I'm using that. So all those wires that you saw, if I quickly go back here, something with some code on it. So for example here, all these wires, thickness, those are each individual classes. That's the only way that I could make that work quite decently. They all have their parents saying, hey, 1D, you're 1D, you're 2D, which then has another parent, which is my object primitive. And so what I'm doing is I'm actually feeding in that object primitive saying, hey, by default, that's the value. And only when you wire in the specific array, it will override that. So if it sees, hey, you're that LabVIEW primitive or that object primitive, don't use it. It's go to the other state or you're in the correct state or whatever. And otherwise, yeah, it will take the value along. So it is the same strategy.
We're finding the same things.
Come again?
I was just saying we're finding the same things.
Sorry, I thought you had the microphone. So I was like any other questions?
Where is GPU toolkit or this VIs?
So you can find it on VIPM. So the GPU toolkit is freely available on VIPM as a community edition. There is also a commercial edition. So the community edition is free. You need to request a free license, Tools Network, but that's it. And there are a couple of limitations. So RT is disabled and so on. And also there's a license agreement in there that says any code that you make, you need to share with the community, making it a community edition.
But it's not shipped with LabVIEW, right?
Come again?
It's not shipped with LabVIEW.
Maybe in a couple of years.
Okay. And what pitfall, how reliable is it?
Come again?
How reliable is this toolkit?
Well, it's my own toolkit, so it might be biased.
What you can and cannot do.
So it is under active development. I have a ton of people using it who are happy. Of course, I'm on the end that when something goes wrong, I get the messages. But I'm going to be quite honest with you, last couple of months, I haven't gotten that many messages anymore saying it's working perfectly, no issues. Of course, if you have an issue, give me a shout, send a contact form, and I'm happy to have a look at the code, give you an updated version, give you a quick workaround so you can hit the ground running. I like to think I'm quite approachable. So if you have an issue, please contact me. Any other questions? Yeah.
So you have wonderful use cases for VIMs. There's a simpler one that can be very useful for a lot of people who are rolling their own queued message handlers. You know, if you're not using something like DQMH or you're not using a number of those other scripted type toolkits, a lot of people, when you're starting your queued message handler, you're talking about your data type, and frequently you're starting with a cluster. Maybe you're doing an enum of here are my specific messages, and then you'll have your data. And that is very hard to generalize because you want that typed enum to give you your cases and make it so that you're not getting spelling mistakes by using a general purpose string. But then if you want to generalize that because you've got 5, 10 different, 100 different state machines, well, you can't, because you either overload your enum to 1,000 different types, or you're back to, hey, let's use a string. Well, if you make your queued messages VIMs and you pass in the enum, you can then just have the format into string handle it as a string, but your in queue message, you can pass in any type defined message you want for state machine A, state machine B, state machine C that all have all of these different enum type defs. And you don't have to have 5,000 format into strings everywhere. So it does help you border some of that reusability versus tendency to mistype something, have an incorrect case, what have you.
I'm searching for the specific, oh, here we go. No, that's not the one.
Exactly.
So this is a great example of just making an algorithm that either safeguards the work for your developer or safeguards the work for yourself. If you make it decent, you can, or if you really think about it, you can make it in such a way that it's constantly reusable. Excellent. Any other questions? Yeah.
It's maybe not related to the topic, but kind of a roadmap of LabVIEW. I'm very interested in NI vision and in control and simulation toolkit. So can you tell what is roadmap?
So vision is already implemented. There's image processing. There's machine vision.
No, I mean what's new and how it's developed.
The toolkit itself.
Yes.
So the roadmap, the basic implementation was implemented about a year ago. Then I added support for adding LabVIEW arrays, a lot of bug fixes initially. Then I added multi-GPU support, so you can communicate with multiple GPUs at the same time, or even have like the iGPU on your CPU and a CUDA card running in parallel. And recently I added LabVIEW real-time support with full CUDA support. And machine vision was also added, I think on version 1.2, I'm not certain anymore. And the next version 1.5 is going to have GPU accelerated controls and indicators.
Okay, in vision, right?
In vision, but also for signal processing.
I see.
So it's a general toolkit. It's not specific for machine vision or large data handling. I have customers who are using that in closed loop systems where you have data coming in at multiple gigabytes per second. They're processing it, and based on that data, they're changing their excitation because the nature of the data in that case didn't work for an FPGA.
And there is classifier there. So any advance in classifier using neural networks?
So there are methods for machine learning and artificial intelligence. However, I have not done that too much work into that just yet because that part of the market is already quite crowded. I prefer to first give you guys more on the test side, the tools you need, the visualization, the data processing, to get started with that instead of doing, in my opinion, a little bit of a tangent to AI and trying to compete there. I am going to circle back on that at a later point, though, once the toolkit has reached maturity where I feel I can start investing time in those parallel tracks.
Okay, and control and simulation?
So actually, the toolkit ships with one example on signal generation, how you can generate signals on the GPU itself to then inject them in your control loops on the CPU if you have a PID or so running there. But if you want to know more on that, I'm also stationed at the Radx booth downstairs, and we can have a chat further if you want, because I think everyone might be saying this is a bit too far away from Malleable VIs.
Yes, thank you.
Any other questions? Yeah.
Just some example of perhaps generally just offloading a task to a GPU.
Oh, yeah, sure. There we go. So for example, here is a simple piece of code. Let me just quickly zoom in. LabVIEW 2024 zooming function, great for these types of things. So I have a simple function just to show you. Well, I have a LabVIEW array, I upload it. This is still an old example. Before I had the function to immediately feed in an array, so you can even ignore the upload array if you want. But this is, for example, a simple addition, subtraction, and dividing by 2 to then grab the data back out. There are hundreds of functions from basic mathematics, Boolean logic, statistics, vector algorithms to sort, to get unique values. There are functions to get the maximum value, minimum value, get multiple maximum value so you can make your own peak detection algorithm. There's actually also an example on that one in here. There are examples on getting multiple devices or using multiple devices in here. I can't zoom there, but so for example, multi-device support is also a feature where you can, for example, say I have multiple GPUs, or I want to use the internal GPU and the external GPU of my computer. That's also perfectly possible.
So in this example, plus and minus run in GPU, right?
Completely on the GPU, and it can be 10 megabytes that's running through it. It can be 10 gigabytes. It doesn't care. As long as you have enough memory on your GPU, it will take it.
In this, how do you determine which GPU you're using? Because, like, you know, if you have your internal CPU versus a CUDA.
Yeah. So let me choosing devices. Here we go. So there are a couple of functions available you can set the technology if you want to use the backend, if you want to use CUDA, if you want to use CPU or even Intel 1 API. You can set a specific device, but you have also the get info string. And what that does is it gives you all the information on all available devices for that specific backend, for that specific technology. And then here I have just a simple function. So if I run this, for example, I say I'm going to override it saying, hey, give me CUDA. And I run this. I might, because this is not really going to be readable. Let me just real quick zoom in. Display settings. There we go. So here you can see now I have CUDA. If I say, hey, I want to use OpenCL, so use the iGPU, this can be done in runtime, by the way. You don't need to recompile. You can then just say run again. And then here I have all available targets. So I have my NVIDIA GPU. I can still use that one with OpenCL. I have my iGPU, that's number 1 in there. There's even options for FPGA emulation, so offloading to the FPGA or the CPU. That being said, I haven't really used the FPGA part yet, so I can't speak on its performance.
What about benchmarking, like what your performance difference is?
You're never going to believe this. So yeah, I can do a quick run if you want. I'll quickly change this to the iGPU. this to a more sensible one for my system. So if I run a benchmark, here you can see, well, it doesn't like being that small. Let me put it here. So as you can see now, first it's doing the calculations on the CPU, so there's support for the CPU if you're doing continuous integration. You often are working with virtual machines, so there's no GPU available. So then you can just run on the CPU. Performance is not going to be great compared to a GPU, but just to validate your algorithms, that's great. Next, it goes to the CUDA card, the NVIDIA RTX, way down there. You see it working, and then you have the Intel ultra high UHD graphics, also doing some work. And this is what it looks like. I'll just quickly widen the lines. So my CPU does about 1 teraflops on all CPU cores. So this is not a single thread. This is all CPU cores running together. The green one, that's the iGPU running. And then the red one, yeah, that's the RTX 4080, that's the big graphics card. But that being said, don't let that red card or that red line dazzle you. This CPU is doing also a lot of other things. It's doing your hard disk management, sending data to file, showing things on your screen, doing Windows, doing a lot of other things. So it's not that you go, well, this iGPU is less powerful than the CPU, so I'm not going to use it. No, they work in parallel. Technically, these charts should be added on top of each other to give you an idea of the real performance of the complete system. So those are some benchmarks. In general, I would say you're getting up to 80, 90% of the theoretical performance of the GPU. So that's what NVIDIA says. This is what we, under ideal circumstances, the ideal amount of number of data, the ideal calculation, what it would get. In general, I'm seeing about between 70 to 90% in the benchmark.
What about maxing out your GPU or your CUDA? Like overloading with too much stuff to do?
You can see it as a buffer. So it will just take longer to calculate. But of course, you can distribute across multiple GPUs. Well, again, if you want to know more, feel free to contact me. So my contact details, I'll just quickly pop them open again. You can find me on LinkedIn. G2CPU is also, there's a website. If you go to g2cpu.com, you can contact me and get more information if you want. And of course, feel free to download it. Just make sure you get the free license. The trial, there's something wrong with the NI license manager when you go into trial version. So you're going to get some weird performance issues. Just keep that in mind. So just get the free license and you're good to go. Well, thank you very much for your time.